Let's look at a second example of using Lagrange multipliers. Not super different. I'm going to keep the constraint set to be the circle of radius 5 centered at the origin. And we'll just look at a nonlinear function so that it's not quite so simplistic and not quite so guessable with pure geometry what the answer would be. Um, so let's just get right into it. We are going to have grad f, gradient of f is some multiple, traditionally using the letter lambda, is times gradient of g. And gradient of f now is whoops, just kidding, is, oh, you know what? I think I'm going to use xy squared because I just noticed that's what's in my notes. There we go. Otherwise, I'll confuse myself. So xy squared, the gradient of that is going to be derivative with respect to x is y squared. Derivative with respect to y is 2xy. Okay, and then that's lambda, and that's going to be times 2x comma 2y. Okay, so let's break that out into scalar equations. Y squared is lambda, 2 lambda x, let's say, and 2xy is 2 lambda y. And I'm going to, I often try to remind myself to include the constraint equation by just rewriting it, saying, okay, that's the package. Now, the constraint equation sometimes does have a special role. It never has a lambda in it in particular, but you don't want to forget it and get confused about why you don't seem to have enough equations. Okay, so it can be tricky to know where to start on these, but this one has a rather special form. You could definitely start with this and make some headway. This one has a rather special form, though. It has y as a common factor, and I want to start with that partly because it's a good idea, partly because it's an easy place to make a mistake. Don't uh, don't divide by y, at least not cavalierly. Okay. Um, Let me show you the most careful way to do it. Sometimes we can be a little bit different from this, but we always have to be careful. The most careful way is if you're tempted to divide by a variable on both sides of an equation, subtract and factor instead. Subtract everything on one side and say, okay, the fact that I was tempted to divide both sides by y, which I know you were tempted to do a minute ago, actually 2y comes out. The fact that I was tempted to divide by it as a common factor means it's a common factor when here, and then I can factor that out. And now I can use the zero product property. Okay, so either 2y is 0, or in other words, y is 0, or x minus lambda equals 0, or in other words, x equals lambda. It was very tempting here to just cancel out the 2's and the y's and just say, oh, x has to equal lambda. That's just simply not true. Either x equals lambda, that's going to be one branch we're going to follow, or y equals 0. Now, if you've already been doing any kind of max-min optimization of multiple variables, you've almost certainly encountered this, the idea that you're going to get a tree structure for your equations, and heck, there's going to be cases, okay? So here we're going to have to deal with both of these cases separately. The or is an incredibly important logic word there. Okay, let me squeeze this in, maybe up here. Not a lot of room on this board. Okay, so either one we can start with. Let's start with y equals 0. You probably want to start with that one because that sort of drops you down all the way to the constraint equation. In this kind of setting where we've only got two variables that we really care about, x and y, once you get a value for one of them, just go ahead and go straight to the constraint equation, and you're just basically done. If y equals 0, then x squared is 25, or x is plus or minus 5. So we've got 2 points, 5 comma 0 and minus 5 comma 0. Okay, and so those are going to be possible extrema. Now in the other example, I should have bothered, but I didn't even bother to calculate what the function was at the extrema because it was so obvious which one was the maximum, which one was the min from the picture. But here we are really gonna go ahead and make a careful list, and evaluate the function at those points. But let's just go ahead and make the list first. Now if x equals lambda, that doesn't tell me what x is or what y is directly, but it's a big break, and it allows us to go into another equation. Notice a rather special thing in this first case, though. I never touched the first equation. It already gave me an answer. I should go ahead and make sure I'm not inconsistent though. Let's go ahead and go back to that. If y equals 0, then lambda x is going to be 0. Okay, so let's actually check that. Well, I know that x squared has to be 25, so x can't be 0. Okay, it does work though, because lambda could very well be 0. Okay, so I'm just going to put a little note here. In this case, lambda happens to be 0. So this is sometimes true that you can get a solution or some solutions for maximum and minima without ever determining lambda, which is kind of funky because we introduced the lambda as a key element of the algebraic technique, and yet we never actually figured out lambda for these points. Okay, now it's not hard to go back like I just did and say, oh, happens to be lambda equals 0. That's actually rather significant, right? If the gradient of f is lambda times the gradient of g and lambda is 0, then in fact the gradient of f is 0. These guys are unconstrained critical points. Usually for constrained critical points, you're only discovering that when you go along the constraint set, I'll use black for my constraint color, you don't get any variation to first order in your objective function. But here, even if I did go off the constraint set left to right from these points, I wouldn't get any variation to first order in f. This is actually an unconstrained relative max or min, or maybe it's a saddle, but it's a critical point, and this is a critical point of f. Kind of not super important to us because from the start we said our entire universe is this circle. If somebody came along and said, oh wait, I need a slightly smaller circle or bigger circle, or just remove the constraint entirely, you would be happy to know that these were actually unconstrained critical points. But that's rather special. It only happens when lambda is 0. Okay, now back to the x equals lambda case. If x equals lambda, now I really better go back to here because that's the only way I'm going to make progress. But very quickly, I get something good. Y squared is now going to be 2x squared. So I've eliminated the lambda. Now I have this just talking about x and y. And of course, in this branch, I haven't yet used the constraint equation. So remember how the logic goes with these kinds of things. In the y equals 0 branch, I dropped down to the constraint equation and used that and got some information. Don't think of the constraint equation as being used up. In this branch, I haven't done that at all. I'm starting fresh. I've used this equation, certainly. But I still can use this one and use this one, and it's a really good idea to do that. So I'll just plug that in. We're getting x squared plus 2x squared, substituting in for y squared is 25. 3x squared is 25. I think I can finally just dump these. Okay. And x is plus or minus 5 over root 3, or if you like to rationalize, I don't think it's a big deal here. 5 root 3 over 3. Okay. And then y, of course, y was equal to, we know that y squared was equal to 2x squared. So y is going to be, or y squared is going to be 2/3 of 25. And so y is going to be 5 root 2 over root 3. Okay. And plus or minus. Okay. So we're actually going to get 6 points of interest here. So we're getting these two, and then we're getting these ones where the y is a little bit smaller, sorry, a bit bigger. Yeah, y squared is 2x squared. The y is a bit bigger than the x. Okay, so we're getting these points as well. Okay, so let's check out the values, figure out who wins. There's a lot of symmetry to this system, this situation. This guy, of course, is symmetric across both axes, and this, if you switch y to minus y, nothing happens whatsoever. So that tells us there's definitely got to be a symmetry across the x-axis. And if you switch x to minus x, only the sign changes, and that's why we would also expect a symmetry across the y-axis as well. Okay, so f of 5 comma 0, of course, is just 0, and really plus or minus. Okay, so these guys both evaluate to 0 because this vanishes on both axes, because when x or y is 0, this is vanishing. And I'm going to show you a nice computer printed picture of it in a minute to finish up. F of 5 over root 3, meep, not a very good 3, sorry, 5 over root 3, comma, plus or minus 5 times root 2 over root 3. These are going to give us the same value because the plus or minus just squares away. So x times y squared, we're going to get, was it 125 times that times that squared. So 2 over 3 root 3. Okay, some funky value. And then what's the last one? F of minus 5 over root 3. And again, plus or minus is going to give me the same answer. Lots of symmetry here. I like examples with symmetry, but that's just because I'm a math guy. That's just going to give me the negative of this. Okay, so these are going to be the minima. Those are the smallest values we're going to get. So these here are going to be minima. These are going to be the maxima. That's where the x is positive. And then these are neither min nor max. They're 0 in between these positive and negative values. So let me show you what the computer picture of it looks like real quick. So this is a contour plot of the f of x, y is xy squared. Okay. And you can see up in here is where their tangents, a little above the 45-degree direction, not very far above. And there's 4 places where that's happening. And then there's also these places where the contour lines seem to kind of go off. Well, there's another contour line that's right along each axis. And that's going to be something that intersects the circle. So this circle is our constraint set. Okay. And let me go ahead and rotate this into 3 dimensions. And we can see what's going on here. Okay. So here I've got, let me see if I get a good perspective. This is pretty good. Oh, that's pretty good. Stop rotating. Okay. So here's the 2 maxima where x is positive. Here's the 2 minima where x is negative. And then there's these zeros here where the value comes down, and right as you're going through on the circle, you can see, yeah, this is really an actual flat point on the surface all along that's the x-axis. It's actually completely flat. The gradient is 0 everywhere along there because, as we know, the gradient was y squared comma 2xy. If y equals 0, that gradient's going to be 0. And so that's what's giving us these kind of funkier points where no matter which direction we vary, we're going to go flat. At these 4 points, the 2 maxes and the 2 mins, you can definitely go lower or higher if you go off the circle. But if you're forced to stay on the circle and look at this funky curve, which is the image of the circle, then you are finding the 2 points that are highest as you trace along the circle and the 2 points that are lowest. All right.